Alrighty, we're going to cover the last lesson of Chapter 5, Making Connections. So today, by the end of the lesson, you should be able to represent real-life situations with sinusoidal equations. Let's look at the first example. The variations in maximum daily temperature for Moose Factory, Ontario on the first day of the month from January to December are shown. Write a sinusoidal function to model the data. Okay, so if we're being asked to model with a sine function, we know that we can pick either sine or cos, and we're going to have to find the A, the K, the C, and the D. So let's start with the A. The A is going to equal our max minus our min over 2. So that's going to be our max. We're just going to look through and see 22.4 minus our min of negative 14 all over 2. So that's going to give us 36.4 divided by 2, which is 18.2 degrees. Let's find our C. Our C is just max plus min divided by 2. And that's going to be 22.4 plus negative 14 all over 2. So that is 8.4 divided by 2, which is, oopsie, 4.2 degrees. Okay, next we're going to find the D. So when we're finding the D, what we're thinking about is, number one, which sinusoidal function we want to use, sine or cos, and whether we need a reflection, etc. And then whether we need a phase shift. So the number one rule is always avoid a phase shift if possible. So if we're starting at month 1, it looks like we're starting at our absolute minimum value. And then we're going up to our maximum and then down again to a lower value. So this does look like it's starting at its minimum and then going up and down. The problem with this is that it doesn't start at month 0. Month 1 represents January. So if we go through this, month 1 is January, February, March, April, May, June, July, August, September, October, November, December, and we need to get back to January, right? A sinusoidal curve, especially the cosine one, starts at its max or its min, depending on whether there's been a reflection. It goes up or down, and then back up or down. So this one is, if this was cyclical, it would be at minus 14.0 again in January. So this would represent January, month 13. So the problem is that we don't start at month 0, which means there is a little bit of a phase shift, even if we do want to reflect and start at our minimum, use cos and start at our minimum. So for D, let's just say phase shift, we are going to have to figure out our period, and let's put off the phase shift for a second because we do need to figure out what our period is. So our period here is going from 1, a minimum, to a minimum. So our period is 13 minus 1, which is 12, and this is months. And our K then is going to be equal to 2 pi over 12, which is equal to pi by 6. Okay. So now our phase shift. Our phase shift is going to be, well, if we visualize this, we're at 1, we're at our minimum, we're going to go up to our maximum, down to our minimum. And so we really did move it over 1 month, okay? So D is going to equal positive 1 if we're using cos reflected. Okay, so you always have to kind of put it in perspective when you're figuring out your phase shift. Decide which function and then whether you're reflecting or not. Okay, so I'm ready to come up with a sinusoidal function here. Did it tell us the variables? If it didn't, we should probably use some let statements. So I'm going to just say here, let M represent the number of months since December, if you will, because we're starting at 1. And let T of M represent the temperature in degrees Celsius. Okay, so let's come up with the equation then. We've got T of M is equal to our A, which is 18.2. I'm going to run out of room here. But I need to add a negative onto that because of the reflection. It's a cos. I need my K, which is pi by 6. And then I'm going to put M minus 1 plus 4.2. All right, M minus 1 time, bracket plus 4.2. Okay, so let's see if we can make a scatter plot of the data. And then it says to graph the model. So what we're going to do is we only really used certain values from this. We saw that it was increasing to a maximum of 22.4 and then decreasing back down to -10 and theoretically at -14 if it was back at January, because of the cyclical or periodic nature of temperature over time. So we didn't use all of the data though, and so we're not sure that this is exactly sinusoidal. So what it's asking you to do is just make a scatter plot and then graph this as well and compare the two. So I'm just going to go to I'm just going to write my equation out again. So that's T equals, I can't remember, negative 18.2 cos pi by 6 M minus 1 plus 4.2. Okay, so I'm going to go ahead and do the off camera. I'm going to go ahead and do the scatter plot because I need to go back and forth. And then you pause, you do your scatter plot, and try and graph T of M as well. You should end up with 2 sinusoidal graphs. Okay, so I'm just going to pause, and then you can come back in a minute. Okay, so the red graph is the, I'm sorry that the quality is so bad, but that's this equation graphed. So I just graphed every quarter and then just filled it in and extended it on both sides. I also graphed the scatter plot so you can see every month there was another point, and I joined those points with a nice sinusoidal curve. You know, it's not that nice, but nonetheless. So now I'm going to just maybe choose a few points to label on my red graph, okay, 5 to be precise. So this is 4 and 4.2, and this is 10 and 4.2. This minimum down here was at 1 and minus 14.0, and this minimum over here was at 13 and minus 14.0, and then we can just do maybe the top one, which was 7 and 22.4. Okay, put the equation on there, make sure you've got that, and you're good to go. So T of M is minus 18.2 cos pi by 6 M minus 1 plus 4.2. Okay. how is the fit, would you say? It's hard, best to look at your graph because mine's not very good. But I would say there is a pretty good fit there. Okay, next question. At a certain ocean bay, the maximum height of the water is 4 meters above mean sea level at 8 o'clock in the morning. The height is at its maximum again at 8:24 p.m. Assuming that the relationship between the height in meters and the time in minutes is sinusoidal, determine an equation that models the height of the water over time. Well, it gave us our variables here. We just need to find our A, our K, our C, our D. So let's start with our A again and think about them. It's at its max at 4 meters. And that's above sea level. And so you know that the sea level is like your equation, your equilibrium, your equation of your axis. So you know that A is 4, and you would know then that your minimum would be at -4. So we don't even have to do a calculation here. We know that our A is 4 meters and our C is 0 meters, right? At the equation of the axis, we are at 0. Okay, so that's our A and our C. Our K, well, let's think about our K. Let's go back to our D. Our D is going to be 0. It's at its max if we use cos, right? Okay, so let's think about our period. The period, it goes from max to max in 12 hours and 24 minutes. Well, 12 hours is 12 times 60, because we want it in minutes, plus 24. So 12 times 60, that's 720 plus 24. So the period is 744 minutes, if we wanted to do that in minutes. And if we want our K then for the equation, it's going to be 2 pi over 744, which is pi over 372. Okay, so we've got our K, and we've got our D, and we've got our A and our C, so we can come up with an equation. So we are going to say, let's see, H of T equals 4. We started at our max, so that's okay. We don't need to reflect. Cos of pi by 372 times T. Oh, I'm sorry, I didn't need that bracket because we don't have a phase shift, and we don't even have a C value, right? So all we need to do here is put the T in, and we're done.